Okay, so what's a Wasm? How many people know what a Wasm is? Nobody. Perfect. Okay, so a little bit about me. You know my name, Paul Milham. I work at WildWorks, and I like this job a lot. I get to work on cool things like Animal Jam, which is a lot of fun. We have a few different games that we work on, and plug, we're hiring, so let me know. Okay, I need some JavaScript-y guys or gals. Okay. But disclaimer, I'm not a member of the WebAssembly working group. I'm not anyone important. If that disappoints you, well, there are no other sessions going on right now, so you're kind of stuck with me. But I'm level 30 in Pokemon Go. Good. Yeah, that's pretty good. Okay, 29 and a half. All right. What's that?
Is that high?
No, you guys. All right. So I just had a baby last month. Right, yeah. He's pretty cute. He's got his dad's hairline. That's fun. There he is compiling his first WebAssembly module. If you squint, you can see the function he's coding right now is named poop, which seems appropriate. All right, so what are we going to learn in this session? So first, what is WebAssembly? We'll have a definition for that. We're going to look at some WebAssembly myths, so things you might have heard about WebAssembly that aren't necessarily true. We'll look at how to load them in Node and in the browser, and then we'll look at some code and how to use it. Look at how WebAssembly and JavaScript talk to each other, so how they interoperate. We'll talk about high level, just some use cases that you might consider for WebAssembly. We're going to look at some languages that compile to WebAssembly and why you'd want to compile to WebAssembly versus hand coding it. Okay, so this is a good summary of what WebAssembly is. WebAssembly, or Wasm, I'll use the terms interchangeably, is a new portable size and load time efficient format suitable for compilation to the web. So this is really exciting. People have been asking for this for a long time. No more ridiculous workarounds where we compile the JavaScript. Okay, we have a proper compile target, which is really cool. And it's fast, it's small, it has a ton of advantages, and we'll look at those. But the important things here is this is assembly for the web. All right, it's binary encoded assembly for the web. Do not come in with fancy ideas like you're getting for loops or something like that. All right, this is low level. All right, you get some matrixy. Yeah, you can kind of see it. All right, anyway, that was supposed to be funny. It wasn't really. So we have a fast and efficient stack machine. So again, very low level. When you're working on this stuff, you're going to be pushing things onto the stack. You add two numbers, push it onto the stack. You can pop it off. It's really low level. If you think back to college, think of MIPS or something like that. But it's safe, open, and debuggable. So that makes it web tech, right? These are all important aspects of web technology. And WebAssembly fits right in. This isn't something too foreign. You're going to see that it moves right along with JavaScript. And the other important thing is it's real. A lot of the times you hear about new technology and it's distant on the horizon or something. WebAssembly is real right now. Open up Node 8, type in WebAssembly. It's there. Open Chrome, Firefox, Safari. It's there. All right, so it's usable right now. The MVP is in browsers, in Node right now, so you can use it. Now, we're still working on Edge. IE will never get there, but, you know, pretty good. So some myths that we'll talk about. WebAssembly is not like a magic wand that makes your JavaScript run faster, right? You code crappy JavaScript, it's going to be crappy JavaScript at the end of the day. If you code good JavaScript, it's still just going to be good JavaScript. WebAssembly has nothing to do with that, all right? There's not a compiler for JavaScript to WebAssembly. I mean, there might be, but JF Bastian, I don't know him, but smart guy on the internet said, the minimum viable product version of WebAssembly does not support garbage collection and JIT capabilities, which make it possible to implement a fast JavaScript virtual machine. An interpreter is entirely possible with clever tricks. It can be quite good, but not as much as what native implementations do. So you're not going to compile your JavaScript somehow to WebAssembly and get faster speeds than you are from a native JavaScript engine. Now, people are still talking about it. People are still attempting it. So, you know, maybe we'll see. But these are pretty core features. They're on the WebAssembly roadmap. But right now, WebAssembly is not doing away with JavaScript anytime soon. Another myth you hear is that WebAssembly is really just for games. Now, if you visit the WebAssembly website, in all fairness, one of the things that they have is a pretty cool little tanks demo, which I'd encourage you to play. It's pretty cool. Anyway, this is a demo of Unity compiling to WebAssembly. And I'm going to throw a disclaimer in here. If you don't work on games, you're pretty much wasting your time. They're the coolest things in the world. So, I mean, computers were built to play games, and then people started doing business and things like that with it, flying to the moon. I don't know. Anyway, so games are awesome. But WebAssembly isn't just for games. There's a lot of interesting research going on in this space. Virtual DOM. Everyone uses a virtual DOM right now, right? Pretty much there's no framework that doesn't use a virtual DOM. And maybe that'll be moved to WebAssembly. It's high compute, and maybe it's a good target for WebAssembly. Another thing is we're JavaScript programmers, right? So anything that's not JavaScript is legacy code. Okay, so any legacy code like C++, you can compile to WebAssembly, and then you can access it from JavaScript. So that's really cool too. You don't have to do these weird little hacks where you're compiling to JavaScript and it takes forever to parse. You have like 15 megs of JavaScript. WebAssembly is a lot faster to start up and a lot faster to parse and run. Sometimes when you go to websites, they start mining bitcoins on your behalf. Well, not on your behalf, on someone else's behalf. Those things are going to be like 10 times faster now. That's cool, right? Okay, maybe not. Anyway, and in Node.js, I've seen lots and lots of modules that are rewritten, and it's just like, hey, there's a native module for this, but I like JavaScript better, and native modules are a headache, so I rewrote this in JavaScript. Hopefully, for those use cases, we'll see them just compiled to WebAssembly. You'll get the speed, you'll get the cross-platform compatibility, and you won't be rewriting your modules. Another thing you might think about WebAssembly is this is all manual memory management, right? You're compiling from C++, things like that. So is it unsafe? Like, or am I going to have like use after free errors? That's not the case. So memory in WebAssembly, the linear memory you have access to is just a JavaScript array buffer. And it's just a normal JavaScript object. That means it's going to be garbage collected like anything else. And it's contained within the bounds of JavaScript memory, right? So you're not going to do some like pointer arithmetic and read into, I don't know, some other process's memory or something like that. That doesn't happen, right? We talked about that. So and it doesn't have access by default to like window or anything like that. So you're not going to download a malicious WebAssembly module and suddenly it's like reading your user's cookies. None of that is possible. WebAssembly was designed to be safe. Another thing I hear a lot, and I even see people get scared about this, like, is WebAssembly going to replace JavaScript? Yeah, maybe someday, who knows? But I mean, not right now. So WebAssembly is really designed to complement JavaScript. And it's impossible to replace JavaScript at the moment. Like, the technical limitations are there. But you should really look at WebAssembly as kind of like a new superpower that JavaScript can use. Especially at the minimum viable product stage, it's not out there to like, just get rid of JavaScript. That's not what's happening. I mean, it doesn't have access to the DOM, to give you one example. So it's kind of hard to program a web app without access to the DOM, right? Okay. So how do we load WebAssembly? Now, it'd be nice if you could do that. That would be cool, right? But you can't, at least not right now. In fact, you can't even require ECMAScript 6 modules, so forget this. But anyway, anybody following up on that, the controversy? No? Okay, never mind. Skip that. So what we have to do is we have to load the bytes. We have to load the bytes from the disk or the network, and then there's a JavaScript API to go ahead and compile that into a module. So you have this global object called WebAssembly, and that's just going to be in your browser. And it has instantiate. So I'm going to show you an example of how to do this. So what we're doing here is I have a module.wasm. This is a binary file. I'm fetching it from the network. And if you're doing this on Node.js, you could either fetch it from disk using the FS module, or you could fetch it from the network, the fetch, polyfill, something like that. But anyway, we fetch it. Then we get the bytes. So just the raw bytes is what we're dealing with here. And we call instantiate on it. And now we have a reference to our module. This is really cool. So we have like some C++ code or something we've written, and now we can access it from within JavaScript, just like it's a regular JavaScript object. Pretty cool stuff. So what does Wasm look like, though? Well, it's a binary format, so if you want to be super cool, you could edit the binary, I guess, but probably not, right? So there are these .wat files. They used to be called .wast, W-A-S-T. I don't know why they changed it to WAT. Maybe it was, I don't know. Anyway, that's what they are, so deal with it, right? So what does it look like? It looks like this. So again, this is pretty low level. Don't expect anything fancy, but let's walk through these lines just real quick. There's a lot of information here. So the very top and the bottom are module. This just declares that we have a module here. And all this function that we're doing, all this module is going to do is just add 2 integers. Don't go home and write this module and be like, my adds are going to be so fast. That's not really true, all right? That's a waste of your time. JavaScript adds numbers really fast anyway. But there's overhead when you call into a WebAssembly module. It's significant. It's very low, but if you're doing something tiny like this, it's going to add up. So anyway, we have a function. We export it so that it's accessible from JavaScript, and we're naming it Addy, just because I like to name things stupid things. And this function, what it does is it takes 2 parameters, and then it returns an integer. Now this is typed. All right, it's not like JavaScript. This is strongly typed. The first parameter, I'm naming it first. That's one of the very few affordances that a WebAssembly will give you as a coder, is you can name your parameters. And that's pretty cool, right? Anyway, so I have first, it's a 32-bit integer, and I have second, it's a 32-bit integer, and this function returns a 32-bit integer, right? So it adds 2 integers. That's great. So now this 5th line here, what we do is we get the local first, we get local second, we push those onto our stack, right? And then we call this add, all right? And that's going to add those 2 together and push the result on the stack. And at the end of the function, whatever's on the stack is returned. So that's how this works. So that, that's kind of painful to handwrite. I wrote a lot of it just because I don't like myself. But let's go ahead and look at how you manipulate memory from WebAssembly. So here, it looks really similar to exporting a function, but we're exporting mem. That's what we're calling it, and it's 8 pages long. Every page in WebAssembly is 64 kilobytes. So you declare this memory, it's linear memory, so it's just like an array buffer that you would put a typed array view on or something like that, and you just manipulate the bytes directly. So we have a lot of memory here, and now we're exporting a function called poke_mem, and that does exactly what it sounds like. It's just going to poke our memory. So at the beginning of the array, that's that const 0, the very beginning of the array, we're going to store const 1 in the first byte, right? So store 8, we're storing a single byte, and we're storing the value 1 in there. That's all this does, right? So WebAssembly is strongly typed. We have 4 types. This is it. Okay, no, nothing high level like a string, all right? We have 4 types. 32-bit integer, 64-bit integer, 32-bit float, and a 64-bit float. We have a stack machine. We saw how that works. We can export functions. We have some linear memory. And we have, I don't know, 60 or so low-level commands. Things like add, subtract, multiply. You can do things like that. You can store values. You can load values. But that's all you get. And so let's save our questions until the end. And so how do we talk to WebAssembly from JavaScript? How do we call exported functions and access linear memory? So let's look at some examples of that. So this is the code we saw at the beginning to just instantiate the WebAssembly module. So that's great. We have a handle on it. Now how do we actually use it? So in module.instance.exports, that's going to give you a reference to all of those things we exported. So in our case, mem and addy and poke_mem, right? And so if we want to call addy, we just call the function just as if it's a JavaScript function. Now, one thing to note here is that there's no await here. There's no callback. This is synchronous. So when you call a WebAssembly module, you're synchronously executing that code, which is pretty cool. So we just get the result back, and we can see that is 3. So our WebAssembly module works. That's pretty cool. How about poke_mem? Let's look at that one. So we call poke_mem, and we're just going to inspect the memory here. So there's exports.mem. That's that export we made. And the buffer is the access to the bytes. And we can create a typed array view on that, and we can see what's in there. And we get 1, so that's cool. We flipped a bit. Congratulations. Okay. So how do we talk to JavaScript from WebAssembly? And how do we import functions into WebAssembly from JavaScript? So if WebAssembly, if it didn't have access to the DOM or anything like that, it would be kind of useless. I mean, you could run some raw computations on it, which is really cool too. But you kind of need to reach back into the DOM, back into JavaScript if you want to do some of the other interesting things. So again, this is the same code we saw to instantiate the WebAssembly module, but when we call WebAssembly.instantiate, we pass a second parameter, which is an object. And this object just has references to things we want to let WebAssembly have access to. So here we're just giving it a log function. Hello from WebAssembly. And this is what our module is going to look like. Again, this is the text file that'll be compiled to a binary file. So these don't actually run in the browser, but we can use this to compile a WebAssembly module. And so here we have this import line. And you can see utils and log, that matches up with the stuff that was passed in. And I'm creating a new function called JSLoggy, and all this does is it uses the call keyword to call that function. All right, so we've got a JavaScript file, we're creating a WebAssembly module, we're passing some stuff in, and in WebAssembly, we're calling back out to JavaScript. So this is just a really simple example of how we can call from WebAssembly to JavaScript. So that's cool. So we just figured out the most inefficient way in the world to trace logs, which is pretty impressive. So obviously you wouldn't do this, right? But this is an example of how you can interface between the two. So this is a real example of something we use WebAssembly for at WildWorks. We've got this customer service tool, and what it does is they can pretty much look up any information on the user they want, including the user's inventory. And our CS representatives were like, hey, it'd be really useful for us if we could actually see the colors of the items they're wearing, see, I don't know, in our game, like some things, like if you have a purple hat, it's worth way more than like a blue hat for some reason. But anyway, so the color is important. And we wrote a decoder for these images. They're in a custom format, and so we wrote a decoder in JavaScript, and it was pretty slow. The naive implementation was actually very slow. It was about like 40 to 60 milliseconds every image we wanted to decode. We spent some time optimizing, and it was still too slow. So it's kind of a bummer, right? I mean, we got it fast. JavaScript really isn't a slouch, especially if you're operating on typed arrays. It's pretty fast. But this is one point where we're like, well, how about we rewrite it in WebAssembly? So let me show you this WAT code here. You can see what it looks like. You guys see this? Yeah, that's pretty good. So, I mean, this, again, I wouldn't recommend doing this. It was pretty painful. And this is not a long file, right? It's like 100 lines. But it's really easy to read in JavaScript, and it's not easy to read in this WAT code. If I did this again, I think I would write it in C or something like that. That's going to be a lot more a lot clearer, a lot easier to read, and it'll probably even perform better. So one thing that WebAssembly is not going to do for you is it's not going to like optimize your code for you. JavaScript is great at that, right? You feed it this crazy language, and somehow it pumps out pretty optimized code, especially when it gets hot. It optimizes it really well. But WebAssembly is not really designed for that. You're supposed to compile to it, get optimized code, and then the web browser runs that. Okay. Yeah. So, oh yeah, I was going to show you one other thing. Let's look at it live. If the network cooperates, I'll show you what this actually ends up looking like. So this is a web application that we wrote for our moderators. Hence, Animal Jam moderator. Okay. So I'm going to go in here and look up some user details. This is my user, so don't freak out that I'm showing you some kid's info or something like that. I swear I'm not 35 years old, though. I don't know how old I am. I don't think it's 35, though. Anyway, okay, so this is all my user's info. But let's say I want to look at this user's inventory. So it's pretty cool. I mean, it runs pretty fast, right? Decodes them, spits them out. So I was pretty happy. This turned into a success story. Before, you'd get a lot of frame hitches while we were scrolling, things like that. But it's nice and fast now. So it ended up working. So this is proof. WebAssembly is actually real. It actually works. That's a pretty cool skull I've got there. Check out that wizard hat. Huh. Okay. Anyway, so that's cool. Man, you guys are not as excited as I was about that. After 3 years of WAT code, or 3 days of WAT code, you'd be excited. All right. So anyway, not 3 years. I'd be fired by then. So WebAssembly, I put warms up faster than JS, but when you run WebAssembly code, it's going to run efficiently very quickly. JavaScript, after so many iterations, it's going to optimize the code, right, and make it faster. But WebAssembly is good about that right away, and it parses really fast too, which is cool because it's a binary format and it's very simple. I'm not like one of the geniuses that thought up how to do all that stuff or even understands it, but it's really fast, which is awesome. Let me show you this. I'm excited about this. Chicken mark. Okay, so chicken mark is the latest in benchmarking. I can say that because nobody else has written a benchmark in the last 2 hours. So let's check it out. So let me explain a little bit about what's going on first, I guess. So I've got two chickens. I got the JavaScript chicken, yellow, WebAssembly chicken, kind of bluish purple. And they need to get their chickies. The chickies are scattered all over, and they need to gather them all up. So what I did is I wrote some kind of meaningless algorithm in JavaScript and then ported it to C. Then I compiled the C to WebAssembly. And so they're both going to run that code. It should be equivalent. And every time they run that, they're running in web workers. So they're running it in parallel. They send a message to the main thread, and then the main thread updates the chicken, has it move around and grab these chicks. Okay, so that's pretty much what it is. So let me show you how this works a little bit. Oh snap! Yeah, let's try this. Aw, dang. Okay. So one thing you'll notice here is that the purple chicken's faster than the yellow chicken. Right? Are you just like blown away? Are you in awe? I don't know. So they're running the same algorithm. This is pretty much the same code. Now this was cherry picked because I wanted the purple chicken to be faster, right? But so they're working to get. Oh, that's a cool glitch. Anyway, so they're working together, getting these chicks, and it's pretty obvious that WebAssembly's fast, right? That was the point of this. WebAssembly's fast. That's awesome. So again, cherry pick. JavaScript is actually really fast too if you tell it to do the right things. There you go. So now there's just a pile of chickens. Yeah. Okay. All right. Anyway, pretty cool. So let's shut that down because my computer is about to launch into space. So, yeah, that's cool. Okay. So, chicken mark. Yes, it's available to license. If your company is interested, come talk to me. No takers. All right. Anyway, so what is WebAssembly good for? Like, why would you use this? I mean, chicken mark is obviously contrived, right? So you would use it in pretty much any time you have a really CPU-intensive task. Anything you can think of that's CPU-intensive, I think, is a good candidate for this. Any legacy libraries you have lying around, anything that's not JavaScript and you want to compile to the web to use from the web, this is also a great use case for this. So some examples I've seen, someone took JavaScript core and compiled it to WebAssembly. That's the JavaScript engine for Safari. They compiled to WebAssembly, so you could actually parse and run your JavaScript from WebAssembly. So that thing I told you to not do at the beginning of the talk, someone has gone ahead and done it, which is great. That's pretty cool. I don't know. This is a really cool example too. If you're a super fast typer, you can get that in, type it in before I'm done. Doing 2D mesh transformations in WebAssembly. This is a really high compute thing. And so it's basically taking a bitmap and then morphing it so it looks like it's moving around, which is really cool too. Again, virtual DOM, which is a really interesting use case. I saw a PR for compiling C# to WebAssembly. I don't know where that's going, but that's cool. There's a really cool game called Funky Carts too. You can run it on Chrome on your phone, maybe Firefox on your phone too. But it's just a little mobile game someone made. They wrote it in C++, used SDL for the graphics, and then compiled to WebAssembly, and it uses WebGL to render. This is actually a really cool example. It runs great. It runs super smooth. It runs really well on your phone. It's awesome. Like, especially if you come from games, the web is amazing, but like JavaScript is really good at dropping frames, right? And so WebAssembly is kind of what we've been waiting for. Like, you can take non-garbage collected code, so it's predictably fast, and run it and get some really smooth running applications, which is awesome. So why would you want to compile to WebAssembly? Why not just write WAC code? Well, it's kind of painful. That's the first thing. There's no programmer affordances. So the only thing I found is that it allows you to name your variables, right? Fancy, right? So yeah, like classes or anything like that. Forget about all that stuff. Don't even think about like for loops, right? It's really low level. And we should think of it as a compile target. If you start thinking about WebAssembly this way, you're more on the right track. And so probably the most developed one, the most mature one right now is C and C++ compiling to WebAssembly. If you're serious about it, you should probably pursue this track. Now, C and C++ have amazing compilers. People have spent, I don't know how long, probably decades optimizing these compilers, making them output really optimized code. And so this is really good. Let me show you this one called Wasm Fiddle. So what this does is it takes C code. You see that? Is that big enough? Yeah. It takes C code, and then it just compiles it to WebAssembly. So let's compile this main, that's a stupid function name. Here, how about foo? That's way better. Okay. So let's compile foo, and we can see it spits out the WAC code right here, so we can read it. And that's pretty much what we'd expect, right? But what if I wanted to make this foo function way more advanced? Okay. Yeah, that's better. That's exactly what I want. So I compile it. Now this is kind of the magic here. You can see this WAC code barely changed, right? Before it was just returning the constant 42. Now it's returning the constant 84. So we don't see that multiply happening up at the top. That's really cool. The compiler was smart enough to say, this is always going to return the same thing. I'll go ahead and do this calculation in advance and just return it directly. This is a very small example of the kind of optimizations the compiler is going to make for you. Okay, cool. So there's some helper libraries out there like Wasm init. Mscripten, you're going to run into this if you start compiling C and C++ to WebAssembly. Rust, this is really cool. This is the official logos of Rust, right? That's from Cars. It's not the official logo of Rust. Okay, anyway. So Rust is a really cool language. I like it. And it has a WebAssembly target. And it's used Rust up. Rust toolchain in general is really cool. I like it. But that's another avenue you can pursue. And there's this whole new family of languages that are sprouting up that all they do is compile to WebAssembly. The one that seems to have the most steam is AssemblyScript. So it's a subset of TypeScript, which makes it super easy to learn. But there's lots of them. There's TurboScript, which has a really cool little turbo snail mascot. I don't know, that might make it worth using right there. But you can just try AssemblyScript in the browser. There's ThinScript as well. I heard Nim also compiles to WebAssembly. I'll be shocked if, like, a couple years from now, you can find a language that doesn't compile to WebAssembly. It's pretty exciting. So what's the point? Woo! Okay. All right, anyway. I absolutely hate transitions in presentations, so I save them all to the end. All right. This is cool, all right? So JavaScript is Batman, WebAssembly is Robin. This is cool. I love it when he punches him. It says, undefined. Okay. Anyway. So, I don't know. This is really cool stuff. WebAssembly is really powerful. It's awesome. It's here now. You can start using it. You know, we should think of JavaScript as having a new superpower, which is really cool. You get to watch them all again. That's exciting. These were the worst animations I could find in Keynote, so, oh my gosh. And I'm not going back. Anyway, So JavaScript is kind of conquering the world right now, right? It's everywhere. I mean, you can use JavaScript to do about anything. You know, they always bet on JavaScript. And now WebAssembly is just piggybacking on JavaScript. It's right there in the browser and the VM with it. Same virtual machine is running WebAssembly as is JavaScript. So I'd say always bet on WebAssembly as well. Now, if you didn't listen to anything else in this talk, but you care about WebAssembly, go to that awesome Wasm list. That is the best resource I found. It's just a list of great resources about WebAssembly. So if you're interested in the topic at all, check out Awesome Wasm. And yeah, that's all I got. Okay, thank you. I'm not sure how.
To take questions.
Yeah, that's fine. But I won't answer questions I don't understand or don't know the answer to.
You said that when you call into WebAssembly from JavaScript that it's blocking.
Mm-hmm.
Why then would it be good for CPU-intensive tasks if it blocks the memory?
Yeah, well, okay. So, I mean, that's a really good point, especially since Node.js doesn't have workers right now. That's something they're working on. So, I mean, you can just make the argument that Node.js in general is not good for CPU-intensive tasks from that angle. And I think that's a fair argument. The point, though, is that you're going to be able to perform those computations faster in WebAssembly than you could in JavaScript. And as soon as we get some sort of threading model in Node.js, I think it'll be fine.
For browsers, though, can you run Wasm in WebWorker?
Yes, yeah. Yeah, we're doing that at WildWorks right now. Yeah. Everybody else WebAssembly now? Oh, go for it.
I was curious about the AV decoder source file you showed.
Mm-hmm.
Did you consciously choose to write that in Wasm, or did you transpile that from C or C++?
No, that was hand-coded as a wet.
What were the factors that went into deciding whether to write it in a C language or whether?
Yeah, so I mean, the biggest factors were just naivete about WebAssembly at the time. And I'm still not a WebAssembly master or anything like that, but I wanted to understand what was going on, what it looked like, and how it worked. And if you want to get code running quickly, the simplest path to follow is just to handwrite it and then compile it. Sometimes setting up the C++ toolchain is a little bit intimidating. That said, I would go that route if I did it again. But yeah, that's pretty much it. It was more a learning experience than it was for the benefit of my company, I guess. Okay, good.
I can keep asking. I was curious about the performance test you had.
Uh-huh.
How did you make sure that those two things were comparable on the JS side and the Wasm side? If we want to write our own performance tests.
Mm-hmm. Yeah, I mean, well, I just made sure they were doing the same things. So they do a lot of stupid things, actually, like counting, finding primes, and then I did array access as well. So it's kind of a hodgepodge of different things.
You count the number of milliseconds that it takes to run JavaScript, and that only allows
Yeah.
WebAssembly that much time? That's blocking, right?
No, oh, okay. So I probably didn't explain that well enough. So there are 3 threads running. One is a main process, and that's actually rendering the chickens and handling the logic that makes them bounce up and down and directs them where to go, things like that. And then there are 2 workers running. So those are completely separate threads. Yeah, and so it's blocking in the worker, but every time that work finishes, it just publishes a message, hey, I finished my work, and JavaScript does the same thing. So they're both tweeting to the main thread that they're done. Yeah.
That's good design, thanks.
Oh, cool. Thank you. Okay, cool. Yeah. Oh,
Were you at Node Interactive last week?
I sure was. How'd you know?
If not now, then after, would you like to decompress that and talk about any cool you saw there?
Yeah, sure. Yeah, I'd be open to that.
Also,
Oh, thank you. No, Node Interactive is my favorite conference. I've been to a couple of them, and it's always really good content. Yeah. Oh, sorry. We can talk about it offline, I guess. But yeah, it's a cool conference. Yeah.
Since the logo's up there and we're recording it, feel free to give them some more marketing.
Yeah.
You want to give them credit for.
No, yeah, absolutely. I would attend if you have the opportunity. It's a great conference. Not as good as this one, obviously, but okay, cool. Good. Thank you. Thank you guys for coming.